All right, let me try another one here. How about chapter 24, number 21? Because this can give some confusion between 21 and, what's the other one, 41. Because 41 is a conductor, and this one they don't really say conductor or not. But they say really thin, so it wouldn't matter, and that's kind of where we gotta read into it. But 21 and 41 almost look like the same answer, and they're not. There's a little subtlety, so I wanted to do both of those for clarity. But reading the problem here for number 21, it says you have a large horizontal sheet of charge. And so if I can kind of draw this, maybe I'll draw something that I'm trying to make look three-dimensional. And I don't know if I should measure a back of this, but if this kind of looks like in your mind this sticky pad here, and say, okay, this is my horizontal sheet, and they're saying there's charges spread out evenly over this whole sheet. Let me encourage you to go back either to the lecture or to example 5 in the survey book, because your author goes through this. And so without me going through the details, he does something like this. He says, make a cylinder. And so here's the sheet, and here's a cylinder. And so he says, take this Gaussian cylinder through there and apply Gauss's law to this, and you'll find the electric field. So if I try to draw that in three dimensions, the cylinder will cut through right about here. So maybe I'll make a dotted line, and the cylinder will go up a little bit, and this will be the top of the cylinder. And then the other half of the cylinder will go down, and so let me draw the bottom part of the cylinder. And in example 5 or in the video lectures, you'll see the argument is made that the electric field would have to be leaving the sheet. These are lines of symmetry, and so they would be sticking up through the top of the plate and then sticking down to the bottom of the plate. I shouldn't say plate. Well, they're going from the bottom of the plate, and then they penetrate outside of the bottom of the Gaussian cylinder. And so this is where the flux crosses the surface, the Gaussian surface, and this is where the flux crosses the Gaussian surface down there. And the author does a good job of coming up with sigma over 2 epsilon naught in example 5. Now, I'll put this maybe over here to the side, but it would be double that had the flux not gone downward, which for a conductor, that's what would happen if I made a cylinder and the bottom half of the cylinder was in the conductor. I wouldn't have that bottom piece. And you can see that in figure 24.9. So we are going to be using this stuff for the conductor, and that's for problem 41. So let me cross it out for here, but hopefully won't confuse you here, because there's another little subtlety step in 41 that you need to see. All right, but focusing on this problem, then I can now find the electric field, and the problem says above it, but this doesn't matter whether it's above or below. It's the same, so that's kind of irrelevant. But the real key, though, is kind of in these words. What does it say here? It says large, and it says you're in the center. And so because of that, it's indirectly telling you that go ahead and use this formula that we derived for an infinite sheet. Even though it's not infinite, it is large. And see, being in the middle means that we're not close to the edges. So I would expect that this equation may not be valid near the edges because it was derived for an infinite sheet. So if you're in the middle of a large sheet, it's probably significantly accurate. So that's the idea. Now the problem's really easy. You just put in your numbers. They said that the charge density was, let me look back here, what was it? 9 times 10 to the minus 6 coulombs. And then they said 21. Oh, Yeah, and that's all we need because this is then 2. And the permittivity of free space is the 8.85 times 10 to the minus 12. The units here are Newton meters squared over coulombs squared. And so looking at our units here, we would get, after that cancels off, a Newton per coulomb from here, and then a times a meter squared. Wait, my bad. This is a charge density. This is per square meter. So square meter should cancel off, yeah. And then that should cancel off because this is the appropriate units, newtons per coulomb for the electric field. Good. Sorry, I almost missed that. All right, so now I can just punch in my numbers here. So grabbing my numbers, I can go, what is this, 9 times 10 to the minus 6. Divide that by 2 and also divide it by 8.85 times 10 to the minus 12. And I get, it looks like a 5.08, 5.08 times 10 to the 1, 2, 3, 4, 5. And so there's the answer. Hopefully it's the right answer. Maybe I should flip over here. Yeah, good. It matches what your author got.